Hello, my name is Krishna Kaloni and I'm a student at Clear Creek High School. Today I'm presenting a simulation-based framework I've developed called the Digital Carbon Footprint Intelligence Framework, or DCFIF, which addresses the challenge of estimating and reducing session-level digital carbon emissions using machine learning and statistical modeling. I'll walk through 6 sections today: the problem, motivation, relevant background and literature, my methodology across several experiments, results from each experiment, a candid discussion of what findings actually mean, and conclusions with a path toward future work. And this is my introduction. Let me begin with the problem. Digital devices and cloud infrastructure currently account for roughly 3.7% of global greenhouse gas emissions, a figure projected to nearly double to 8% by 2030 if current growth trajectories continue. What makes this particularly challenging is that environmental cost is largely invisible to end users, even though it's directly shaped by their behavior and computing choices. A gap in existing research is that prior approaches tend to treat estimation, optimization, and behavior change in isolation. No prior framework integrates all 4 components: real-time carbon prediction, uncertainty quantification, personalized behavioral recommendations, and carbon-aware scheduling into a simple computational pipeline. The aim of this project was to build exactly that: a 7-experiment simulation platform using 2,000 synthetic sessions and a suite of algorithms including gradient boosting, random forest, Monte-Claro simulation, k-means clustering, ANOVA, compound growth modeling, and Gaussian naive Bayes. I want to be upfront about the key limitations from the outset. All data is synthetic. This is not the real device or cloud telemetry. The carbon formula is known and pre-specified, so the machine learning models are approximating it rather than discovering unknown physical relationships. Time of use multipliers are simplified into 3 fixed tiers. Real-world validation is future work, and I've tried to be explicit about this throughout. And now the background. The literature supporting this work falls into 5 thematic streams. Firstly, early ICT emissions research treated digital infrastructure as a static carbon contributor with fixed emission factors. This work was by Hussein and Zhu, established these baselines. Second, machine learning methods, particularly random work and gradient boosting, emerged as tools for modeling nonlinear relationships between CPU load, memory, network traffic, and carbon output. And then third, carbon-aware scheduling research demonstrated that shifting workloads to low-carbon period grids is one of the highest impact levers available without degrading performance. Fourth, probabilistic methods, including Monte-Claro and Bayesian approaches highlighted by Lacoste, improved trust in carbon estimates by surfacing uncertainty rather than masking it. And fifth, found that personalized feedback is significantly more effective than generic strategies for influencing user behavior. This research gap addresses is that none of these streams have been integrated into a unified computational pipeline, which is exactly what this framework attempts. Now, slide 7. The methodology. The synthetic dataset consists over 2,000 sessions generated with random seed 42 for reproducibility. The carbon formula is additive, where CL is carbon intensity and TF is a time of factor use assigned by hour of day for peak off-peak hours, 1 for standard hours and 1.45 for red peak hours in the evening. Variables were sampled from distributions designed to reflect real-world computing. Diversity. Device power across 4 profiles from laptops to workstations. Session duration uniformly distributed from 30 minutes to 4 hours. Data transferred from a heavy-tailed exponential distribution and carbon intensity drawn from a range reflecting multi-region grid variation. The mean baseline of carbon across all sessions is 1.592 per session. Gaussian noise was added to labels to make the ML estimation task realistic. Now the experiments. Briefly, the 7 experiments each test one hypothesis. E1 uses Monte Carlo simulation to quantify uncertainty around point estimates. E2 compares a static ridge baseline against random forest and gradient boosting. E3 applies k-means, clustering to the test whether personalized interventions outperform generic ones, and E4 measures the carbon impact of shifting sessions from peak to off-peak hours. Now, E5 uses one-way ANOVA to test whether a cloud workload type predicts carbon output. E6 applies compound growth modeling to test project emissions under business as usual and reduction scenarios. And finally, E7 tests a Gaussian naive Bayes classifier and a session risk categorization baseline. Now the results. First, the results of Monte Carlo uncertainty. Starting with E1, using 500 Monte Carlo samples per session, the mean 95% confidence interval width was 1.026 kg, approximately 64% of the mean session carbon value. This is meaningful because it confirms that reporting a single point estimate on a user-facing dashboard is misleading. For higher carbon sessions, the interval widens proportionally, which has direct implications for how uncertainty should be communicated in any production system. Now model 2. E2 is where I want to be particularly careful about honest interpretation, because corrected conclusion differs from a naive reading of the results. Across RMSE and R squared, the static ridge model actually wins. Achieving R squared equals 0.965 and RMSE equals 0.178. Gradient boosting achieves the best at MAE at 1.31, but does not outperform Ridge overall. Random forest performs the worst on RMSE and R squared. The reason is straightforward, because carbon is generated from a known additive formula. A linear model with the right features fits it well. Tree-based models are not discovering a known structure. They're approximating a formula that Ridge can already capture. That said, ML remains useful in real-world settings for 4 reasons: handling noisy telemetry, where formula inputs are unavailable, supporting real-time inference without direct measurement, providing interval feature importance, and extending the nonlinear effects not present in the simplified formula. Featured importance from random forest confirms that session duration, time of use factor, and carbon intensity are the most dominant predictors. And this is continued feature importance of random forest. Now E3, the personalization. E3 validated k-means at k equals 3 using the elbow method, silhouette score, and Davies-Bouldin index. 3 behavioral clusters emerged: 2 streaming high-heavy profiles and 1 device-heavy profile with higher average emissions of 2.2 kg. Personalized interventions achieved 11.9% average reduction versus 10.78 for the generic strategy, a gain of 1.17 percentage points. This is the modest per section, but consistent across clusters and potentially meaningful at population scale. Statistical significance testing is recommended before making stronger claims. Now E4, peak versus off-peak temporal scheduling. E4 produced the largest simulation intervention effect, a 44.62% carbon reduction from shifting workloads from red peak hours to green peak hours. I want to flag the important caveat here. The result is particularly structured. Moving from TF equals 1.45 to TF equals 0.65 produces a reduction of roughly 0.45 by construction. The result illustrates the potential of temporal scheduling, where real-world validation would require continuous hourly grid carbon intensity data, rather than the 3 fixed tiers used here. And now E5, cloud workload variability, also known as ANOVA. One way ANOVA on cloud workload type yielded F equals 247.74, overwhelming statistical evidence that workload type is a dominant emissions predictor. Memory-heavy workloads averaged 1.717 kg, compute-heavy averaged 1.593, and balanced workloads averaged only 1.1. This has direct implications for cloud resource allocation policies. Growth prediction. E6 applies compound growth modeling at 8% a year. The correct 2025 BAU value is 2.338 kg CO2 per session, not 2.228 as originally stated. The corrected calculation is 1.592 times 1.05, which leads to 2.338. Under a DCFIF reduction scenario, applying 11.95% annual savings, this falls to 1.238 kg by 2025, a difference of 1.1 kg per session. Now classification through Gaussian naive Bayes. This is baseline only, but E7 presents a Gaussian naive Bayes classifier that categorizes sessions as safe, warning, or critical, based on carbon thresholds. It achieves 56.8 accuracy, significantly above the 33% random baseline, but not suitable for protection deployment. The primary failure mode is warning critical confusion near the 1.81 kg CO2 squared boundary, driven by the correlated features that violate GNB's conditional independence assumption. The recommended upgrade phase is light GMB, or a 2-layer MOP, which is estimated to achieve 78% accuracy. Now, this is the key metrics of all of the experiments at a glance. The summary metrics are R squared equals 9.65 for the static model, 44.62% scheduling reduction, a 1.17% reduction point personalization grade, and F equals 247.74 from the ANOVA, and a corrected BAU growth of 2.338 kg by 2025. Now the discussion. The synthesis here is that simple interpretable models are surprisingly competitive on synthetic formula-generated data. This is not a failure on the framework, it's an honest finding. In a real-world deployment where formula inputs are unavailable and nonlinear effects are present, tree-based models will likely outperform linear ones. For algorithm recommendations, random forest is preferred for real-time inference, given its low latency and interpretable feature importance. Gradient boosting is better suited for offline batch carbon auditing, where its MAE advantage matters. Monte Carlo confidence intervals should always accompany point estimates. In the scheduling policy, combining green hour assignment with k-means behavioral segmentation produces the largest simulated reductions. Limitations. 6 limitations are worth restating. MO is approximation as known formula rather than discovering physics. The carbon model excludes PUE and embodied carbon, and and cooling load. TF tiers are fixed rather than continuous. G and B is a weak baseline with no comparison to strong classifiers, and the personalization gain was not tested for statistical significance. Now the conclusion. All 7 hypotheses were supported under simulated conditions. The corrected conclusion for E2 is that the static model achieves best R-squared and RMSE with gradient boosting competitive on MAE only. Looking forward, the most valuable next steps are validating the framework with real cloud logs and device telemetry, testing light GMB and MLP classifiers for session risk alerting, placing fixed TF tiers with continuous hourly grid carbon intensity data, and exploring deep reinforcement learning for adaptive real-time scheduling. Longer-term extensions can include temporal fusion transformers for 24-hour carbon forecasting, graph neural networks to propagate carbon through microserve chains, and federating learning for privacy-preserving personalization. Thank you. The core contribution for DCFF is a transparent simulation-based pipeline that integrates estimation, uncertainty, quantification, personalization, and scheduling into a single framework with the honest acknowledgement of its current limitations and a clear path toward real-world validation. I'm happy to take any questions.